Today we're going to talk about how to tell whether a function is continuous or not. There's three things that have to happen in order for a function to be continuous. Here's the first one. F of c has to be defined. C is just going to be some x value that they will tell you. The second thing is the limit as x approaches that x value has to exist. The third thing is that the limit that you find and this first thing that we found, f of c, they have to equal the exact same thing. So those three things have to occur for a function to be continuous. If it's not continuous, you have to say which one of these it did not meet. Down here, a definition. A function is continuous on an open interval, and in class we'll talk about the difference between open intervals and closed intervals. But it's continuous on every open interval if it's continuous at every point in that same interval. And we'll talk about more about that later. Okay, so remember, here are the three things. This one right here, this right here, and this right here. These are the three things that must happen in order for something to be continuous. So we're just going to look at the different examples and state which one of these it does not meet. So here's our first example. If we'll just look at this, okay? First of all, the easy way to tell if something is continuous or not is when I trace this, do I have to pick my pencil up in order to trace the entire function? This one I do. I'd have to pick up my pencil, so I know it's not continuous. But I just can't say it's not continuous because I pick up my pencil. I have to use a mathematical reason why. This one, the limit would not exist. Remember, here's my three things. F of c exists. F of c in this point, and they're talking about, in this case, c is 2. So f of 2 is, I think they're going by halves here, 1.5. So it does have a value there. But my limit, which is this one right here, doesn't exist because I have this big gap, right? So this is not continuous at this point. Let's look at this one. This is continuous at c. Again, 2 is what they're talking about. If I trace this with my pencil, I never have to pick it up. So this is an example of a continuous function. This is another example of a function that is not continuous. If I trace it, I'd have to pick up my pencil where that hole is to keep on going. So let's see which one of these it doesn't meet. Does f of c exist? Yes. There's my f of c. Does the limit exist? Yes, but my limit is whatever this point is right here. This is coming in from the right. I follow my graph, but it doesn't follow this third one. My limit, which in this case is, it looks like 1.5, does not equal f of c, which it looks like, what is my y value, 0.5 probably? They're not the same. Here's another example. This is not continuous because I cannot trace it without picking up my pencil. So we have to figure out which one of these three does it not have. So let's try this one. Does f of c exist? So in this case, c is 2. It's my x value. Do I have a value when x is 2? No. So it's not continuous here because f of c does not exist. All right, so let's look at the next one. And again, I think these are just the same types of things. We're looking at graphs. We're going to say yes or no. Is it continuous? If it's not continuous, why? So I can automatically tell this is not continuous. All right? The reason is, and let's read it right here, f is undefined at c. The limit does exist, but it's not continuous. All right? The rule was that very first rule. F of c does not exist. F of 2 does not have a value. This is not continuous. All right, again, I'd have to pick up my pencil. Why? Well, I have this huge jump in my graph. The limit doesn't exist. For something to be continuous, the limit would have to exist. On this one, again, I can tell it's not continuous because I have to pick up my pencil. Let's see why. The limit would exist. My limit is, looks like 1.5. f of c exists, there's my point, but those two things do not equal the same thing. This one is continuous because I can pick up my pencil. the limit exists, it's 1.5. F of c exists, it's 1.5. And so, yes, it is continuous. All right. Now we're going to talk about the different types of discontinuities. There's basically two different types, removable and non-removable. When you have a non-removable, it's either going to be a jump discontinuity or an infinite discontinuity, and we'll talk about that. Let's look at removable discontinuities first. Here are two examples. Removable discontinuities is where you have a hole. I know this is not continuous because when I trace this, I'd have to pick up my pencil. Okay, but since it's just a hole, I could actually fill that hole in to make it continuous, so that is a removable discontinuity. Same thing here. Here's a graph, has a hole in it. That is an example of a removable discontinuity. My next two examples, these are going to be non-removable. So anything other than a hole is a non-removable discontinuity. Okay, non-removable discontinuities, there's two different kinds, jump and infinite. Jump discontinuities is exactly what it looks like. There's a jump in the graph. Okay, here's this big jump or that big gap. That's an example of a jump discontinuity. Same thing with this one. That's a jump discontinuity. Infinite is where you have vertical asymptotes. This is not a continuous function because I'd have to pick up my pencil. I have this vertical asymptote that looks like at 0. So this would be called an infinite discontinuity. Same thing with that bottom one. Looks like I have a vertical asymptote right through here. So this would be an infinite, which is a non-removable discontinuity. Okay, so that's just some kind of terms that you need to know. All right, so let's look at some examples. First thing I'm going to do is find the limit as x approaches 1 from the left-hand side. So I'm going to follow my graph. I want to know, what is my graph approaching from the left? Well, it's approaching this number, even though it's not circled in right there. It's approaching that y value. So that's going to be 0. The limit as x approaches 1 from the right-hand side. Same thing. I'm going to follow my graph from the right until I get to where I want. And I almost said that they're wrong here, but they're going by halves again. So that is as 1, x equals 1. Again, my y value is approaching 0. So we know from our previous lesson that if the limit from the left equals the limit from the right, then the total limit is 0. So now they want to know, what is f of 1? F of 1 means when x is 1, what is your actual y value? Again, they're going by halves here. So that value right there is 1. So then they're asking me, is f continuous at x equals 1? I automatically know that it's not continuous because if I trace this graph, I have to pick up my pencil. So I can say no, but then I have to say why. And I have to put one of those 3 reasons. Does f exist? Okay, so does f of 1 exist? Yes, at this point. Does the limit exist? Yes, we said the limit was 0. But f of 1 and my limit as x approaches 1 are different. So that's what I'm going to put. F of 1 does not equal the limit as x approaches 1. So we can't just put no. We have to put why it's not continuous. Okay, let's look at another one. Evaluate the limits. I want to find the limit as x approaches 0 from the left. From the left, I get closer and closer to 0. That's going to be negative 1. Find the limit as x approaches 0 from the right. As I come in from the right, it's going to be a positive 1. So does the limit of 0 exist? No, because my two limits were not the same, and I have this big gap in my graph. Does not exist. F of 0. Okay, what is f of 0? And this point, and we're going to assume that these are open circles here. They didn't really tell us. Okay, or one could be closed, one could be open. It doesn't really matter. I'm going to put does not exist. So I think down here, they're going to ask us, is f continuous at x equals 0? Well, we can automatically tell by looking, no, because I couldn't trace it without lifting up my pencil. But then I have to say why. Well, there's two reasons why. F of 0 didn't exist, and my limit didn't exist. So you can just put one of those if you want. F of 0 does not exist, or the limit as x approaches 0 of f of x does not exist. All right. Okay, this one's a little bit different. Here's what they've given us. They've given us a piecewise function, but they've left out this coefficient in front. So they want us to find what this number would have to be that when we graph these two things, it makes it a continuous function. So basically, whenever I graph these, we want these two equations to match up at x equals 1. So here's what we're going to do. I'm missing this a here. We know that these two things have to meet each other at 1. So here's what we do. 3x cubed. And that's going to have to equal this function at 1. Okay? Well, I'm going to go ahead and set those equal to each other. But I know at 1, when x is 1, they have to meet or they have to be the same number. So that's why I set it equal to each other. So let's plug 1 into my x's and solve for a. So 3 times 1 cubed equals a times 1 plus 5. So 1 cubed is 1. We have 3 equals a plus 5. Subtract 5 from both sides. So I know when a is -2 that these two functions would match up and they form a continuous function. Alright, so a would be 2, so I'd have 2x plus 5. A is the answer that we would be looking for though. So anytime you have a problem like this where you're missing the number and you want to make this a continuous piecewise function, set them equal to each other, plug in your x value, and solve. Example 4, find the domain for each function. Where is each function not continuous, and what kind of discontinuity is this? So on your notes, we highlighted how to find where a function is discontinuous. The very first one said set the denominator equal to 0 and solve. Well, this one I don't have a denominator, so I don't have to worry about that. The second one talks about a trig function. The third one says to find a hole. This one doesn't fall into any of those. I would graph this. So graph this in your y equals. And when you graph that in your y equals, you're going to get something that looks like this. It's going to be the absolute value, I'm sorry, not absolute value, the square root function moved over 2 places. So it's going to look something like that. Now to remember what domain is. Domain means what are your x values. So if I scoot it over to -2, my domain starts at -2 and it's going to go to the right, or it's all the numbers greater than -2. That's my domain. Where is this function not continuous? Well, if it starts here, are there ever any breaks in my graph after that? There's not. So where is each function not continuous? I'm just going to put it's always continuous. I'm not even sure what they would have in the back of the book. So as long as I know what my domain is, I'm going to say always continuous. And what kind of discontinuity is this? We won't even have to answer that question. Okay, so let's look at this one. Find the domain of each function. Domain are our y values. It's the same place of where it's continuous. So on your notes, it says to find points of discontinuity, or to find where a function is discontinuous. Set the denominator equal to 0 and solve. So look at what I'm going to do. X squared plus 5x minus 6 equals 0. Now to solve this, there's lots of ways you can do it. You can use the quadratic formula. You can factor it, which in this case is the easiest thing to do. I want factors. That's going to be what? X plus 6, x minus 1. Set each factor equal to 0. It's a 0 there. X equals negative 6, x equals 1. Alright, so I know that it's going to be continuous, or find the domain. Let's write our answer for that first. I'm going to write it up here. My domain, there's lots of different ways you can write this. This one, it's going to be all reals except where we found these 2 points, except x equals negative 6 and x equals 1. So that's one answer. Where is each function not continuous? Same place. Okay, it's not continuous, so I'm going to put discontinuous at x equals negative 6 and x equals 1. What kind of discontinuity is this? Well, if you're not sure, graph this original function and see what happens at negative 6 and negative 1. You should see this. 1, 2, 3, 4, 5, 6. You're going to have these vertical asymptotes. This isn't real neat, but you'll get the idea. And I think when you graph it, you're going to have something that looks like this. Let me look here. Yeah, it's going to cross. Let me change. It's going to look something like this. It's going to go up. It's going to look like this. My markers aren't. Something like that. And like this. That's the graph of that. Right? So, what kind of discontinuity is this? It's an infinite discontinuity. So that's what you would write because I have vertical asymptotes there. This looks really, really messy. That's okay. It's an infinite discontinuity. Alright, tangent x. We want to find the domain. Where's the function not continuous? And what kind of discontinuity is this? So graph this in your calculator. When you graph this in your calculator, you're going to see something that looks like this. Make sure when you graph it that you're in radian mode. And tangent x, this is also on your basic graph sheet that you have, looks something like this. And it just keeps repeating itself. So I know that this is not continuous because of all these breaks in the graph. The domain is, we're always going to put all reals except. The except will be wherever these vertical asymptotes occur. So if you're not for sure, probably the easiest way right now, if you look at your trig chart that I gave you, on that trig chart, if you look at tangent, find the first place that tangent is undefined. It's undefined, I'm going to write down here, at 90 degrees. Then the next place it's undefined is 270 degrees. Then if I kept going, because our chart stops at 360, the next one, what they have to do, they added 180 to this. The next one would be whatever this is plus 180. Then I could do another one. I could do another one. So it's going to be all rails except 90 degrees, 270 degrees, and then I could keep on going. Instead of writing 90, I'm going to write pi over 2, because pi over 2 is the same thing as 90. Then I need to write a way that it's going to be every number after that, every 270 plus the next one, plus the next one. So I have to figure out what did they add to this every time to get that next number. They added 180 degrees. 180 degrees is the same thing as pi. So I'm going to put all reals except pi over 2 plus every pi after that. So plus pi, and then every one of them after that, we write that as pi k, because it's 1 pi after that, 2 pi after that, 3 pi after that, 4 pi after that, and that's just a shortcut to write that. Where's the function not continuous? not continuous at pi over 2 plus pi k. What kind of discontinuity is this? Since it's vertical asymptotes there, it's an infinite discontinuity, which is also a non-removable discontinuity. I think that may be the last one. Yep. So your assignment is on your note sheet that I gave you, and it's also on Blackboard, and I'll answer any questions in class.